Well, good day, everybody. This is Chris back again with the Ancient Scholar, and now today we'll be going into video number 6. 6 whole videos on receptors so far. And today what I'm going to do is I am going to now talk about the sympathetic nervous system versus the parasympathetic. So we're going to talk about the sympathetic, all right, the sympathetic nervous system. And the sympathetic nervous system has alpha and beta receptors. And alpha and beta receptors, specifically the alpha, that's just a symbol for alpha, the alpha 1, the beta 1, and the beta 2 receptors. Now, these receptors have different physiological effects that we've already talked about, but because they are all acted upon by a specific class of molecules, okay, we call these sympathetic. All right, we call these sympathetic receptors. Okay, sympathetic receptors, or sometimes we may even hear the term adrenergic. Oops, let's do that again. Adrenergic. Adrenergic receptors, okay? And an adrenergic receptor, I just think of ad as in adrenaline. Adrenaline, okay? So these are all receptors that are acted upon by adrenaline, okay, or adrenaline-like molecules. Adrenaline-like molecules. All right. Even though they have different responses, they're all agonized by adrenaline or adrenaline-like molecules. Okay, and these adrenaline-like molecules are what are known as catecholamines. So Catecholamines, catecholamines. Catecholamines are adrenaline-like molecules, and the other name for adrenaline is something called epinephrine. Epinephrine is another name that means adrenaline. And adrenaline, the reason we call that is that we know that adrenaline is secreted by the adrenal, adrenal, the adrenal gland. And the adrenal gland, ad just means on top of or above, and then renal means kidney. So the adrenal gland is the kidney on top of, or the gland on top of the kidney. So the adrenal gland, one of the hormones the adrenal gland secretes is adrenaline, and another name for adrenaline is epinephrine. Now, nerves, sympathetic nerves can also produce epinephrine or adrenaline. So epinephrine is both a neurotransmitter and a catecholamine. But when epinephrine activates alpha and beta receptors, I get that sympathetic response. I know it's kind of confusing and there's a lot of different terminology there. And molecules that are chemically similar to adrenaline or epinephrine are called catecholamines. So what we're going to do is I'm just going to kind of throw up here a picture of let's do epinephrine, okay? And epinephrine has two kind of major parts to it, kind of like the acetylcholine, where the acetylcholine has the acetyl group and the choline group. Catecholamines, or all adrenaline-like substances, also have two primary components to them. Actually, three primary components. But and if you've watched my respiratory therapy playlists where I talk about these, you probably already know this. But let's just go ahead and review it. So the first part is something called the benzene ring. And the benzene ring is a very common structure in biochemistry, mainly because it's so incredibly stable. Okay, so the benzene ring consists of carbon atoms, and those carbon atoms are bound together in this ring-like structure here. Okay, so each of these points is a carbon, and then of course you have hydrogens and stuff that come off of that. And then every other bond on the inside of this ring is a double covalent bond. Okay, so it's going to look something kind of like this, and then like this, and like this. And the thing is, you don't know if it's this is the double, this is the double, this is the double, or this is the double, this is the double, or this is the double. It's because these electrons are kind of spread out, you don't really know, but we just draw these. And what this means is this is what's called resonance structure, where it kind of resonates, and maybe it's this, this, and this, and then at another time it's this, this, and this, but it kind of resonates back and forth. And I'm not here to talk about resonance structures and all that, but this structure is very stable. The benzene ring is a very stable substance in biochemistry, so it should come as no surprise that very important molecules like hormones and neurotransmitters are built upon the benzene ring. Okay, so that's one part of it. And then from the benzene ring, I have this little side chain, carbon, hydrogen, CH2 over here, an NH, and then I believe a CH3, and then I believe I have a hydroxyl group that comes off of this here, and then I have some hydroxyl groups, HO here and HO here. Okay, so the catechol, the catechol, when I say catecholamine, refers to what we call the catechol nucleus, or the benzene. Okay, the benzene ring. That is the catechol part, and then the amine. And anytime you hear the word amine, okay, amine, I always think of amino, A-M-I-N-O, amino acid. And amino acids, of course, are formed using nitrogen bonds. Nitrogen bonds are kind of the backbone of amino acids. So the amine part is this side chain here, the amine side chain, because I have nitrogen right here. Okay, so that makes this an amine side chain. And then the two hydroxyl groups that come off of this side of the benzene ring are also characteristic. Okay, so what I drew here, this is actually the epinephrine. Okay, the epinephrine, or the adrenaline molecule. Okay, now I can alter this structure slightly. Okay, I can alter this slightly, and it's no longer epinephrine, because it has to look like this is epinephrine. It's no longer epinephrine, but it is still a catecholamine, because it has the benzene ring, the amine side chain, and the two hydroxyl groups here. But I can modify this slightly. And let's just do that. Let's do something like this. Okay, so I'm going to draw my my benzene ring here. Let's do an OH group here. Hydrogen and nitrogen here. And from that nitrogen, I'm going to have CH3, CH3, CH3. CH3, or we call methyl. Methyl is just a CH3 group, okay? And then I am going to have a hydroxyl group here and a hydroxyl group here, okay? And I'm just going to draw a circle to designate that there's resonance there. Okay, so I still have a benzene ring, I still have an amine side chain, and I still have my two hydroxyl groups. But you can see that the amine side chain has been changed just a little bit, and the hydroxyl groups have moved slightly. Okay, so you see how the hydroxyl groups are here, here, and here, but on this molecule, I've moved a hydroxyl group. I don't have one here, and I've moved it up here and changed the amine side chain just a little bit. This here is an example of a molecule known as albuterol, okay, which is a molecule that we give as a medication. Actually, we give to people that have lung disease like COPD, chronic obstructive pulmonary disease, asthma, and this is a catecholamine because it is like epinephrine. It's epinephrine-like molecule, so it's kind of a catecholamine. But its action is different. It is different from epinephrine slightly because we've modified it. And so epinephrine acts upon all of the the sympathetic receptors. So it acts on the alpha 1, it acts on the beta 1, and it acts on the beta 2. It has very strong generalized sympathetic effects. So if I give somebody epinephrine, I'd expect the heart rate to increase, the blood pressure to increase, I'd expect shunting of blood, I'd expect jitters, anxiety, I expect bronchodilation, I expect the whole range of sympathetic effects to occur. But let's just say that I don't want all of those effects necessarily, and I just want to focus on opening up bronchioles in the lungs, okay, because that's my patient's problem. I don't want to give them a lot of epinephrine. I could, we can give epinephrine, but there are lots of side effects. So instead what I'm going to do is I modify the epinephrine molecule a little bit, and I have this albuterol molecule, and the albuterol has high affinity, okay, so it wants to attach not necessarily to alpha and beta 1 receptors, but it has the highest affinity for beta 2 receptors because we've modified the catecholamine structure slightly, and we're making albuterol is then going to attach to the beta 2 receptors, going to have the highest affinity for those receptors, and it won't affect the alpha 1 and the beta 1 receptors as much, and that's one way that we can make make use of the whole lock and key analogy a little bit, that this is a slightly different key than epinephrine, so it'll affect different receptors differently, and in the case of albuterol it does, and you don't have as many side effects when you administer albuterol. So that was just kind of an overview of the sympathetic receptors. The one that I like to focus on is that beta 2, just because a lot of medications that we administer affect beta 2 receptors, and the beta 2 receptor, I should say, is a metabotropic. And specifically it is a G protein coupled response that occurs. So it's a metabotropic receptor with a G protein coupled response. But it is activated by epinephrine. If you remember the last video, we had metabotropic receptors that were G protein coupled, but they were activated by acetylcholine. So you can see that this can rapidly become very complicated very quickly. Okay guys, I'm going to go ahead and cut it off here. As always, thanks for hanging in there.